On August 21st, 1945, a young physicist named Harry Daghlian was working alone in a laboratory at Los Alamos. It was late evening. He was performing an experiment with a sphere of plutonium surrounded by tungsten carbide bricks, building what we called a critical assembly. He dropped a brick. The brick fell onto the plutonium sphere. For a fraction of a second, the assembly went supercritical. A brief flash of blue light filled the room. Cherenkov radiation, visible to the naked eye. Daghlian received a dose of approximately 510 rem. He died 25 days later. His cells stopped dividing. His bone marrow ceased producing blood. His intestinal lining disintegrated. His skin sloughed off. He remained conscious almost to the end. I knew Harry Daghlian. I knew many people who died from radiation exposure. I understood the physics of what killed them better than most. Let me explain exactly what happens when ionizing radiation enters your body. What radiation actually is. Not all radiation is dangerous. The light from the sun is radiation. Radio waves are radiation. The warmth from a fire is radiation. What kills you is ionizing radiation. Radiation with enough energy to strip electrons from atoms, to break chemical bonds. There are four main types relevant to nuclear physics. Alpha particles are helium nuclei, 2 protons and 2 neutrons bound together. They cannot penetrate skin. A sheet of paper stops them. But if you inhale or swallow an alpha emitter, it destroys tissue from inside. Beta particles are high-energy electrons. They penetrate through skin into shallow tissue. A few millimeters of aluminum stops them. Gamma rays are high-energy photons. They pass through your entire body. Only thick lead or concrete provides meaningful shielding. Neutrons are the most biologically damaging per unit energy. They penetrate deeply and cause secondary radiation when they collide with atoms in your body. When any of these enters your body, the same basic process occurs. The radiation deposits energy in your tissue. This energy ionizes atoms, strips away electrons. These ions are chemically reactive. They attack molecules that your cells need to survive. The target? DNA. Your body contains approximately 37 trillion cells. Each cell contains a complete copy of your DNA, approximately 3 billion base pairs, encoding the instructions for everything your body does. Ionizing radiation attacks DNA in 2 ways. Direct damage occurs when radiation strikes the DNA molecule itself. A gamma-ray photon can break the sugar-phosphate backbone of the double helix. It can knock bases off the strand. Indirect damage is more common. Your body is approximately 60% water. When radiation passes through tissue, most of it hits water molecules. Ionizing radiation splits water molecules through a process called radiolysis. The water molecule, H2O, breaks into highly reactive fragments. Hydrogen radicals, hydroxyl radicals, hydrated electrons. These species exist for only microseconds, but they are extraordinarily chemically reactive. Hydroxyl radicals attack DNA viciously. They break strands. They oxidize bases. They create lesions that the cell's repair machinery cannot fix. A single cell receiving 1 gray of gamma radiation will experience approximately 1,000 single-strand breaks in its DNA, approximately 40 double-strand breaks, and thousands of base modifications. Your cells have repair mechanisms. Enzymes constantly patrol DNA, fixing damage. Most single-strand breaks are repaired within minutes, but double-strand breaks, where both strands of the double helix are severed at nearby locations, are much harder to repair. The cell loses the template needed for accurate reconstruction. Repair attempts often introduce errors. If the damage rate exceeds repair capacity, cells die. If damage is repaired incorrectly, cells may become cancerous. Dose and effect. Radiation dose is measured in sieverts, or rem in older literature. 1 sievert equals 100 rem. Below approximately 250 millisieverts, effects are probabilistic. You may develop cancer years later, or you may not. There is no immediate illness. At 1 sievert, you enter the range of acute radiation syndrome, nausea and vomiting within hours, a latent period where you feel better. Then the illness begins. At 2 sieverts, approximately 5% of exposed people die within 30 days without treatment. At 4 sieverts, approximately 50% die. This is the LD50. At 6 sieverts, approximately 90% die, even with treatment. Above 8 sieverts, survival is essentially impossible with current medicine. Above 20 sieverts, death occurs within days from neurological damage. The 3 syndromes, acute radiation syndrome, manifests differently depending on dose. The hematopoietic syndrome affects the blood-forming system. Bone marrow is extraordinarily sensitive because its cells divide rapidly. Radiation preferentially kills rapidly dividing cells. At doses of 1 to 6 sieverts, bone marrow damage dominates. Stem cells die. Production of new blood cells drops dramatically. Red blood cell counts fall, causing anemia. White blood cell counts fall, destroying the immune system. Platelet counts fall, preventing blood clotting. Victims bleed spontaneously. Death typically occurs 2 to 8 weeks after exposure from infection or hemorrhage. The gastrointestinal syndrome occurs at doses above 6 sieverts. The intestinal lining replaces itself every few days. Radiation kills these rapidly dividing cells. The intestinal lining breaks down. The barrier between gut contents and bloodstream fails. Bacteria enter the blood. Severe diarrhea, dehydration, sepsis. Death occurs within 1 to 2 weeks. The cerebrovascular syndrome occurs at doses above 20 sieverts. Blood vessels in the brain become permeable. Cerebral edema, seizures, death within hours to days. The demon core. The plutonium sphere that killed Harry Daghlian killed again. On May 21st, 1946, Louis Slotin was demonstrating a criticality experiment. He was using the same plutonium core, by now nicknamed the demon core. The experiment involved lowering a beryllium hemisphere over the plutonium sphere. Beryllium reflects neutrons. Slotin was holding the hemisphere with one hand and a screwdriver in the other, using the screwdriver to maintain a gap. The screwdriver slipped. The hemisphere dropped. The assembly went supercritical. The same blue flash. Slotin immediately knocked the hemisphere away. But he had received approximately 1,000 rem, 10 sieverts. He knew immediately that he was dead. He died 9 days later. Nausea within minutes, a brief improvement, then collapse. His white blood cell count plummeted. His hands blistered. Internal bleeding began. His intestinal lining failed. He remained conscious for most of it, describing his symptoms to doctors with clinical precision. 7 other people in the room received lower doses. 1 died of leukemia 19 years later. The demon core was melted down shortly after. Why repair fails? Your body receives radiation damage constantly. From cosmic rays, from radon, from potassium-40 in your own bones. Your cells repair thousands of DNA lesions every day. Why does acute radiation syndrome overwhelm these defenses? At background levels, the cell might receive 1 double-strand break per day. Repair enzymes fix it within hours. At 1 sievert, each cell receives approximately 40 double-strand breaks in seconds. The repair machinery is overwhelmed. Errors accumulate. Cells with too much damage trigger apoptosis, programmed cell death. When too many cells die, tissue function fails. The tissues most vulnerable depend on rapid cell division. Bone marrow produces billions of new blood cells daily. Intestinal lining replaces itself completely every few days. When radiation kills the stem cells, the tissue cannot regenerate. This is why radiation syndrome has a latent period. The mature cells already in your blood continue functioning for their normal lifespan. You feel better, temporarily. But no new cells are being made. Then existing cells reach the end of their lifespan. They die. Nothing replaces them. Systems fail. The Tokaimura accident. On September 30th, 1999, at a uranium processing facility in Tokaimura, Japan, 3 workers added too much uranium to a tank not designed for criticality safety. The solution went critical. A sustained chain reaction began. Blue light filled the room. Hisashi Ouchi received approximately 17 sieverts. At 17 sieverts, his bone marrow was destroyed immediately. Doctors attempted stem cell transplants from his sister. His chromosomes were so damaged that the transplanted cells could not produce functional blood cells. His skin began to fall off. He was kept alive with intensive intervention for 83 days. His family ultimately requested that resuscitation not be attempted. The case demonstrated the limits of medicine. You cannot transplant every tissue. You cannot repair chromosomes shattered beyond recognition. Fallout and internal contamination. Fallout presents a different threat than immediate radiation. Fission products are intensely radioactive. Fallout particles are small enough to inhale or ingest. Once inside the body, radioactive isotopes become internal emitters. Different isotopes concentrate in different tissues. Iodine-131 concentrates in the thyroid gland. After Chernobyl, thyroid cancer in children who drank contaminated milk increased dramatically. Strontium-90 concentrates in bones. Chemically similar to calcium, it irradiates bone marrow for years, causing leukemia. Cesium-137 distributes throughout soft tissue. Plutonium, if inhaled, lodges in the lungs. Lung cancer is the primary long-term risk. Iodine-131 has a half-life of 8 days. Cesium-137 has a half-life of 30 years. Plutonium-239 has a half-life of 24,000 years. The Chernobyl firefighters, on April 26, 1986, Reactor 4 at Chernobyl exploded. Firefighters arrived within minutes. They had no radiation monitoring equipment. They walked through graphite debris from the reactor core. They received lethal doses in minutes. 28 plant workers and firefighters died of acute radiation syndrome within 4 months. Vasily Ignatenko received over 11 sieverts. His wife stayed by his side. She described watching his body change daily, his skin darkening, peeling. He died 14 days after the accident. Long-term effects. The Hiroshima and Nagasaki survivor studies provide the most comprehensive data on long-term radiation effects. Over 90,000 survivors have been followed for decades. The data show clear dose-response relationships for leukemia and solid cancers. At 1 sievert of exposure, lifetime cancer risk increases by approximately 5% above baseline. Children are more vulnerable than adults because they have more cell divisions ahead of them. The physics of harm. A lethal radiation dose deposits very little energy. 4 sieverts deposits approximately 4 joules per kilogram. For a 70-kilogram person, about 280 joules total. 280 joules is the energy in lifting a 30-kilogram weight 1 meter. It would not perceptibly warm your body, yet it is lethal. The lethality comes from how that energy is distributed. It is deposited in discrete ionization events, individual atoms stripped of electrons, individual molecular bonds broken. The energy is small. The information damage is catastrophic. This is why radiation is invisible. It causes no immediate pain. You can receive a lethal dose and walk away feeling fine. Hours later, the nausea begins. Days later, the bleeding. Weeks later, death. Conclusion. Radiation kills by destroying information. The information in your DNA. The instructions your cells need to divide, to function, to live. Ionizing radiation breaks the molecules that encode it. It overwhelms the systems that repair it. When the information is damaged beyond repair, the machinery of life fails. Your bone marrow cannot make blood. Your intestines cannot absorb food. Your immune system cannot fight infection. Harry Daghlian, Louis Slotin, the Chernobyl firefighters, the hibakusha of Hiroshima and Nagasaki. They all died the same way. Radiation does not distinguish between enemies and friends, between soldiers and children. It simply ionizes. It simply breaks bonds. And the body cannot survive without that information intact.